Okay. Good evening all. So in this lecture I will be taking on DEM modeling and simulation of particle flow. I am Dr. Bhupendra Ghodki, Assistant Professor Grade 1 in Agricultural and Food Engineering Department. Right. So what do you understand by this DEM, the term DEM? Do you have ever heard of it? Okay, right, discrete element method. So there are different numerical modeling approaches for in the case of food process, say any process you need to model, say a fruit juice is there. So a juice is basically a, you can say a liquid, right? So it is a continuum matter, right, like water. So and some particles are there, say you are filling the grains in the silo. So they are discrete particles are there in the grains when you put on the grains from the say a hopper, right. So based on that also we can say there are two approaches, right. The first one is continuum approach, right. It is, we can see a continuous matter is there on the right side, a flow of fluid is there in the channel, right. So this space, it is based on the continuum mechanics, and you can divide this in the form of the grids, right, since these are the continuous matter, right. And on the each grid point you can solve the partial differential equations, right, PDEs based on some model, right. So but in the case of this discrete, we have some discontinuous matter. On the right side of the slide you can see I am pouring a cumin seed from a vessel, right, from top to the bottom of it, right. So you can see there are some particles, right, of the cumin. Those particles can be represented by the individual particles, right, which are represented here as a spherical grain, all right. So this spherical grains they have some interaction properties, all right. So these properties needs to be defined. When you model this single particles, individual particles, we can see a bulk behavior of the particle while simulating or modeling, right. So this is what we do in discrete element method, right. Now what is DEM? In this slide you can see we can define this as a way of simulating discrete matters so that we can see the bulk behavior of the particles. In this we can do both the kind of motions, a rotational one and a translational one, right. Suppose I am hitting a ball which is stationary, what sort of motion do you guess, right? I am hitting a stationary ball with a rotational ball. What are the properties that may interact with the, say, this geometry or with the floor? Friction, correct. Density, true. Poisson's ratio, your coefficient of restitutions, you told most of the things. What do you understand by coefficient of restitution?
It tells the particle elasticity as well as the velocity behavior of particle after and before collision.
Yes, it is the relative velocity of particle after the collision. Say the two balls are colliding, just their relative velocity after the collision, then before the collision, divide by before the collision. Okay, so it gives you that. So it may represent as a loss of kinetic energy in the motion, right? It represents actually. So its value is between 0 to 1. Okay, 1 is perfectly elastic and 0 is inelastic. Right? So these are some of the properties which we take into picture, right? And here we define the displacement and rotation like I told. Okay. Now in this slide, this is showing the overview of the DEM, right? Where we can apply it, right? So you can see it is in the automotive industry, pharmaceutical industry, we can apply it over there. While say in a pharmaceutical industry, you need to put on the tablet, making a tablet with the powders, you can apply DEM. In the agriculture, mineral processing, right? And say on the right side, you can see a harvester or a spraying machine is there with a grass over there, right? You can put on a tractor, like which is related to the agriculture, right? The interaction of the tractor tire with the soil, right? Then the spraying of the liquid chemicals on the crop, right? So we need to see the patterns also, right? But this is through continuous matter approach, spraying and all, right? And the sieving process on the very right of the slide, I can see, yeah. This one, Okay, it is not connected. Okay, so this is the sieving on the right side. It is grain sieving. Yeah, just Professor Kingsley was talking about a little earlier, right? So this is showing the types of software which are available in the commercial market as well as in the open source. On the right side, they are the open source softwares, right? On the left side, it is the commercial software. So let us see, it is the DEM which is there. It is now acquired by Altair Group, right? Rocky DEM is there, Newton's DEM, right? And PFC. These are the commercial codes which are available. Right? On the right, if you want to try your hands on, there are some open source softwares also, like Yade, Lights, ACES Particle, and Mercury DPM. In this slide, you can see DEM modeling in grain fruit handling, an overview and processes, right? So I defined this in two forms, right? Free flowing grains, right? In free flowing, the example is taken as filling and discharge of the silo, and there are n number of researchers who did the work, right? Likewise, in the confined grain, conveying can be done, cleaning and separation is one, all right? Impacting of the grain kernel, or impacting of the fruit during the transport. Say I am transporting an apple, right? So I need to see the impact during the transportation on the apple. Is there any damage on the apple, a bruise damage or so? So that can be done through the DEM, right? Silo probing, compression and shearing, and grinding. So grinding, I did my work, most of the work on it, and in the compression and shearing part, say you are pressing some grain in the universal testing machine, so that can be a compression and compression part, right? Then in the grain drying and the 3D printers, like in the 3D printers, powders are there, it is spread on the bed and so on and so forth. So this process also can be modeled through DEM, or you can simulate that, right? Provided you need the input properties, right? You need to define in the software, right? We will take care of that, right? I will show a slide later on. Here you can see, like I was talking about the apples and all during the transportation on the top right corner, right? In the center, you can see on the top there is a compression of, that is a black pepper seed, right? And I saw the force deformation characteristics, right? I prepared a seed with the small balls with some bond properties, right? Then on the left side there is a conveyor, bucket elevator with a flow of grain. On the right, again sieving of the wheat grain is there. Then conveying on the bottom side of the slide. In the center, you can see the grinding, how the particle moves within the grinder, right? And the in the left corner, you see the fibers which are moving on a conveyor. So coming to the fundamentals of the DEM, right? So what happens before DEM, and now what will happen after the DEM? Before DEM, we are solving the equations. There are some empirical equations, thumb of rules are there, and you can see in the top left side of the slide there are vectors, okay? We define the normal force, tangential force, likewise for the velocity, and we find the resultant force, all right? But with the DEM, we do the virtual testing. We can change the design or the dimensions of the machine, right? We can put on the grain, right? We can even change the feed rate, and if we are interested in the discharge rate, we can do that, right? And of course, this reduces the cost, So a little background of this evolved with the molecular dynamics, where transitional part is there, and in 56 and in 79 it was now discrete element method. You can see that the size and the shape of the particle, it can be varied in discrete element method, right? And there is a rotational degree of freedom is also involved, right, in DEM, which is not there in molecular dynamics. So in this slide, you can see the particle J on the top, which is hitting particle I, and the breakage of the forces are there, right? Two particles are colliding, right? So the force, you can define that in normal and tangential direction, force acting on particle I due to some particle J which is hitting it, right? Yeah. Oh, you can't see. Oh, no issues. Which is, now you can break this, right, in normal and tangential direction, the forces. Then there are forces due to rotation also, right, torques, I can say. So this is governed by Newton's second law of motion, and you can represent it by some contact model, which is on the right. You can see represented by spring and dashpot, and the two elements, two particles are connected with a slider which is in blue color. Okay. So force equal to mass into acceleration on the bottom left first equation, right. This force are broken down into different component of spring and dashpot, and then normal and tangential direction. Likewise, the torque, the second equation, torque, you can see moment of inertia and omega v, right. That is rotational velocity and moment of inertia multiplied, right. So this whole cycle it repeats for a certain time steps, right. So this is the basically the background of it, and this contact model is dependent on the part of the application we are doing. We can develop our own, right. So to calculate the forces or the contact forces when the material come in contact with each other, right. So in the software, basically most of the software has this part. They have a kind of creator, right, then simulator, then analyst. In the creator, like you are talking about, we need to define the properties like coefficient of restitution, coefficient of static friction, right, coefficient of rolling friction. And do you think it should be between particle and geometry alone?
No sir, particle to particle also it is involved.
Okay, particle and particle interaction is also there. All right,
The surface also.
particle and
Which surface paper?
yeah, surface geometry of the material. So how will you define, how will you find or determine the particle-particle interaction for the, or say the coefficient of restitution for between the particles? Is there any way?
Two particles are there, so like as you told, like velocity before, after collision divided by before.
But the impact is very, say say in a mill it is moving very fast, or the impact is at very high speed. How to determine that? Any guess? There are special cameras, right, slow motion and high speed cameras kind of, right. So they can do frame by frame, and there are other ways of doing so. This is by the calibration test that we will discuss, right. Say particle density is there, we can find it out, right. So coefficient of static friction between the a grain particle and the wall, say stainless steel wall is there, right. So we can easily find it out via some standard methods, right. But the, say, coefficient of this your friction, right, between the particle and particle, again it is difficult to find, right. So that in that case we need to do some sort of calibration test. So once we put in the properties with a certain contact model, we need to define or import the geometry, our own geometry. Say in this case a screw conveyor is there and material is fed from the top side, right, at certain feed rate of say 2 kg per hour or so, right. And we need to define the rotation, direction of the rotation of this screw, right, at what speed we are expecting it. And for example, I am interested in the discharge rate. So that then there comes the analysis part. So I can put on a bin on the bottom side and find the discharge rate of it, right. Say I can find the mass or the number of particles with certain time, within certain time, so we can get the rate, right. So this slide shows the overall thing, right, in the DEM modeling and simulation part. You need some input parameters that are there, appropriate physics, that means this is the contact model, we need to define that. On the top you can see the particle shape, like in the earlier lectures it was talked, right, you need to define the particle shape. The shapes are little different, we may get a different result. Of course, there are variation in the results, say it can vary from 10 to 40%, depends, right. So if it is a sphere, it is very easy for us to do so, right. So if it is an oval shape, right, so they on the top you can see the shapes are formed by clubbing different materials, different spheres. And then we can also define the particle size distribution. Say my particle size is varying between 9.5 mm to 10.5 mm. So we can define that, right, while feeding also. Now another important criteria is the time step, right, where we also call this as numerical time step, right, in the simulation. So in this numerical time step, right, this is the minimum time which is taken while iterating this, right. So it is defined by the Rayleigh time, right, Rayleigh wave. This wave is the surface wave, we can define its speed by this formulae on the right side. If you know the speed, we can find the time also. So, this is relay time which depends on the diameter, right, coefficient, diameter of the particle or the radius of the particle, density, right, shear modulus, right, Poisson's ratio of the particle. So, once this is defined, we can give the time step, and it generally varies between 10 to 40% in the case of food process or food grains, right. So, what if I put on the higher side or the lower side of this, right? Let us see this by an example. On the right side, I took in my simulation 10% of TR, right, that is the time step. So, you can see a very good behavior of the particle interacting with the conveyor. On the left side, I put it as 50%, rest of the thing I did very well, say I put all the input parameters or the coefficients, right, I put it in a nice way, but I failed it here. So, I cannot do my simulation. You can see the particles are scattered, right, there is no interaction between them. So, this is also a very important thing, right. So, like I told, there are different contact models. In this slide, you can see force and overlap of the two particles, how they are interacting. Say overlap is higher, it is defined by JKR model, right. It means it is more adhesive. Our sample is more adhesive. Then I will select JKR model, which is an inbuilt model, right. And we can develop our own model and we can put it in through API, right, application processing interface. And then there is on the top, there is good greenish color line, you can see Hertz Mendelian model. It is generally for freely flowable particles, right. So, we generally select this one once we are interested in free flow of the particle, right. So, this contact model selection or developing our own contact model, we can do and put it on through application processing interface, and this is dependent on the applications most of the times, right. Say I am interested in the dry granular material flow, I will select Hertz Mendelian model, right. And I am if there is a cohesion, I may be interested in JKR. If it is not solving the purpose, I will develop my own model, right, or you can develop your own model. And then heat transfer, it is limited to the conduction part only, conduction, heat transfer between two particles via conduction only, right. If say you are purging some gas, hot gas, blowing it through the blower from on the top of the grain, right, on the top of the grain you are blowing it, right, and for the drying purpose you are using. So, DEM alone cannot do all the job, you need some say CFD part also for the, since this is the fluid which is flowing in a continuous matter and we need a coupling of them, right. Then bonding model, this is right, bonded particle models are there, right, to create a bond between the internal particles. Right. Then if you are interested in electrostatic part, that is also there, so you can do. Now, the shape representation that I was talking about earlier, right. In this shape, you can see a maize grain on the top, right. And it can be represented by say joining the 5 particles, 7 particles, 11 particles. What do you think, if it is computationally intensive or expensive process to use larger number of particles? It is time taking. So, what we can do? It should not affect our final result, right. Accordingly, we need to select them, right. And on the bottom you can see a pepper seed, a black pepper seed is there, right. And I was interested in the grinding part, right, and we were taking the bond, I chose the bonded particle model and defined certain stiffness, and I chose certain number of particles based on the force deformation characteristic in the UTM, universal testing machine, right. So, here are 522 particles, and again on the back side of that we did a X-ray imaging of that, right. Based on the X-ray imaging, we find that there are some percentage of the pores, say for example 20% pores are there, pore space is there in the pepper, and 80% are the solid particles. So, based on those 80% of the particles, we developed the bonded particle model for the whole grain, right. So, it is made of fully solid, right. Like coefficient of restitution, say we need to find the coefficient of restitution between particle and particle. So, we can do this by some sort of geometry, making the geometry via some calibration test. Here we selected a rectangular box, defined all the properties, and the box, on the front of the box, it is removable. The plate is removed by putting it, right, and it flows down. It flows down, right, it passes away. So, we need to quantify also, we need to cross verify this. Right. So, we tested it with the angle of repose finally. Once the grain moves out, we simulated the same condition in the actual in the software, and we find the angle of repose and the height of the seat retaining the wall. So, that initially in this test we can say, yeah, if it is matching, we will go for the bulk or the larger number of the particles we can go on, right. That means our input parameters, the varying by guessing the parameters, if they are doing well in the simulation, we can take them and move forward, right. And in the powder, there a powder rheometer is used by a researcher, and they match shear this coefficients and all with the their graph, force and deformation characteristics in this simulation as well as in the rheometer, right. So, they cross check the results and then they use it for further analysis, right. Now, let us see some of the application of DEM simulation in food engineering and technology. Like this, in this example, this is for the grain silos, right, a filling of the grains from the top of the silo, right. Say 100 ton of silo is there, it is filled, right. We are interested in the compaction and other studies that we will see, right. Then there is a stagnant zone, rest phase is there. Now, at the time of emptying also, once the bottom pan is removed, right, you can see the discharge pattern of the grains, right. In this we can do different testings, right, how to design the silo, or our silo is correctly designed or not. Like you may be aware of the rat holing in the silo. Rat holing issue? Okay. What it is? Mass flow and funnel flow. Okay, pipe flow, yeah. So, say a stagnant zone in rat holing, a stagnant zone is created on the two sides of the silos, right, due to compaction also, right. And then if you open the bottom of the silo, the top grain will move out first, right, due to piping funnel, right, due to funnel flow. So, that is not desirable. So, you can go on in the depth of this case, or you can study this, right. So, this is in this you can see how it is taken at the micro zone or the particles too, right. Then grain sieving process, here you can analyze the throughput of the grain, you can change the sieve without actually designing it, right. And right, you can do it for the other particles also, not only restricted to the wheat, you can take other grains too, right. And this I had taken for the cauliflower grading, right, a cauliflower grader is there, right. The source of this is an DEM community, right. So, in this cauliflower grading, what they are doing is they develop their own cauliflowers with binding little particles with in the shape of the cauliflowers, right. And then they see the throughput and optimize the efficiency of the system and the processes. This is just to give you an overview of the overall the things which are happening, right. Then this is the case of the potato grader. To see the damage in the grader, there is a conveyor, it is falling on the bottom of the bin, right. And in some cases to fix the height of this conveyor, right, it is used. And it is widely used in the grain drying process. You know, in the mixed grain dryer, this for the grains, there is a loss of around 8% of the non-uniform drying, not a loss, I must say. It is a non-uniform drying of the grain, and some of the grains we cannot eat. So, that means there is a loss, right. So, in this slide you can see a hot air is blowing from the center of the chute, right, and on the bottom you can see that it is heated up, right, the temperature is higher. This shows the temperature profile of the grains, right. So, we can change the design of this, right, a little bit, or the blow of the air, but again we need both of the things, not only DEM, we also need some finite volume method or CFD thing, right, coupled together. Now, this is the case of the cryogenic grinding of spices in single slide. I am explaining this. This is my research work overall. I did it for around 3, 4, 5 years or so. Right. On the top, you can see a pre-cooler is there. Right. It cools down the grain and brings the temperature of the, say I took a pepper spice to a very low temperature, say minus 80, minus 100 degrees C, right, before falling this into a grinder, which is on the bottom side, which is a hammer mill. Okay. So, cryogenic grinding is a low temperature grinding process where we use some sort of cryogen like liquid nitrogen. Right. So, on the top, from the top of the conveyor, we are feeding the grain, say at a rate of 2 kg per hour, and we are interested, the grains are cooled down and it is falling in the mill, hammer mill, right, and it is then broken down. So, this thing is modeled and simulated in DEM, right, via DEM software. Right. So, on the right you can see we made an acrylic sheet, transparent sheet is there, and we observe the flow of the particle in this screw conveying type of device that we call as pre-cooler, but there is no purging of the liquid nitrogen. We are interested in the moving of the grain as well as the conduction between the contact models, between the two particles. Right. You can see with the simulation time on the bottom side you can see within 129 seconds of the simulation or the flow of the particle, it is still at minus 196 degree or so. Right. We assume that the temperature of the particle at the entrance is close to minus 196. Right. Then with the motion, you can see with the geometry, that is the stainless steel geometry, some of the particles are heated up. Right. Their temperature is increased. It is around minus 79 or minus 50 degrees C. Right. So, this is with the Hertz-Mendelian model, which is with the heat transfer conduction model, we clubbed together, right, and we provided the parameters. This is how it looks like in the simulation. Right. I think it is not playing. Let's see. On the top you can see the simulation time, right, 150 second, 200 second. And the grains are entering from the hopper, top of the feed hopper, and it is passing through this conveyor. Right. And you can see the temperature changes within the particles, each particle. And then it is coming from the outlet. And the temperature on the right side you can see most of the grain it is around minus 70 to minus 80 degrees C and close to minus 50 also, right. So, this is just an example. What do you think, what is the actual time which is required for doing such sort of simulation? That depends on the machine, of course. Yeah.
We are using
For an
generally like for 1 second of real time, approx 1 hour.
you have to, yeah, that is right. It took around 1 to 2 hours depending on the system we are using, and you can see only the simulation time which is showing us 325 seconds. Right? So, it is most of the time consuming if you do not have a good system, right, with you. You require a very good workstation with you, right, or a high end computer. Then once enter the mill, right, like I told, we developed a bonded particle model for the pepper. Right. On the left bottom side, you can see the bonds within the pepper seed. Right. This is shown by the red and some cyan color, right, and bluish color. It is through the vector diagram. Each particle is represented by the vectors, and we are compressing this particle in a universal testing machine, and we observe. You can see within side the force deformation characteristic of the particle. Right. I selected 500 particle, 1000 particle, binded them together with some properties of the particle, right, the bond properties that we say. Okay. And then once it matches with the force deformation characteristic, we put those properties in the mill, right, and you can see the scattering of the particle, right, within the mill, how the particle breaks down. In actual practice in the mill, you can see it is very within the fraction of seconds the particle will be broken down, but we cannot see even with the camera. right? Even with a high speed camera we cannot see. Particularly in the case of cryogrinding, if you put on an acrylic sheet, there will be a gaseous nitrogen also there. Again, it is blocking your gaze, right? So then how to validate this? We did with some sort of quantified qualitative and qualitative analysis as well, and quantitative analysis of the particle as well at the outlet of it, right? Again. Okay, so this is the bonded particle model which we developed for a single grain. Then you can see how I took 50 particles. Each particle is having around 500 particles. 50 into 500 you can calculate, right? And with the bond properties and the Hertz-Mendelian model, right? So you can see the particles which are broken down on the bottom side of it is there is a seed, right? So it took around 73 days to me to do just this job. So it is really time consuming. That depends again on the machine, right? So this is the qualitative test, right? There is a feeder on the top, right? We removed the feeder, and you can see the sticking of the particle there, and it is similarly true in the case of your simulation results, right? And then we took those particles and measured the weight, and we can't measure these numbers, so we did it by the weight and cross verified it with the number of the particles, right? And based on this breakage study, right, we find that within this simulation time of 5 minutes, right, initial 0.2 seconds are the particle we assume as the whole particle, and after that some reduction in the size, then again the reduction in the size, okay, and we measure the temperatures of it, and there is a variation of around 25 to 40%, right, between the simulated result and the actual results. And the temperature is measured by placing the thermocouples on the 3 sides of the mill, right, left, top, bottom, right. So what more we can do, right? This DEM can be coupled with FEA, finite element analysis, right? FEA. In FEA you can get the structural analysis, right, while DEM will do the part of this discrete particles and all, and they can be coupled with each other, and you can see the realistic behavior of the particle in say a conveyor or a hopper there. Then it can be coupled with DEM and CFD, right? Like this is a grain dryer. The grains are there, which is taken care by the particles, right? And the hot air is blowing, so you need a CFD part too. But we can interplay with this, right? We can change this. It can be used in the drying, fluidized bed drying, mixing, right, and others and similar applications we can say, right. So in summary, we can say we can predict the bulk behavior of the grain by modeling each and every single particles with DEM, right. Any questions? If you are interested in this topic, I had written a book chapter, and you can go on reading this, right. If you have a question, I am very happy to take it. I cannot cover this in the 1 hour class, but it needs much time. Okay, yeah.
Sir, while doing the simulation, is there any need to calculate time step?
Yeah, you can cross check the time step. Okay. There is a formula for calculating. There is a real time step. You know the formula. You know the properties, right? If you are you find the real time step as say 1 second, and like we told, for most of the cases we take in between 20 to 40% or so. You can put it on in the simulation, right? That time step that you got, right? It will automatically calculate in the software actually.
Yes.
But if you want to find it by yourself, you can do that. Yes. If it doesn't work, you need to take a lower time step, right? Iteration time. It is mostly true in the case of the very high speed particles.
Yes.
Right. Yeah.
And my another question is, like you taught us a methodology, rectangular box.
Yeah, that one. Yeah.
So it is necessary before simulation?
No, it is not necessary at all.
Yes.
Right? since there are not the standard methods for in the case of the food grain, there are variety of the food grains,
Yes.
so it can depend. And there also we need to consider the wall effect between the grain and the wall, right?
Yes.
So for designing that, you need to consider other aspects too.
Okay. Thank you, sir.
Okay, thank you. Any other? Yeah, Dr. Singh.
Hello, sir. What are the
Yeah.
what are the application in pharmaceutical purposes?
In the pharmaceutical purposes, you are asking?
Yeah, for the capsule and all.
For a
like
capsule and all,
encapsulation,
right.
Yeah.
Right. When you make capsule, capsule filling machine is there, right? And you are mixing some drugs in the capsule, right? And if you want to see really a capsule is made with it or not, right? And the interaction of the particle. So this can be done since this is the case of the powder, and you can make a capsule, right? Even you can see the interaction of the capsule with the packaging material, the mechanical behavior, right? While the transportation also. Yes. Since I didn't work in this same area, but just you can go on in this case. I was expecting something else from you. You talked about earlier we interacted with in the case of the fruits, right? Fruit and vegetable transportation. Yeah. Anyways, is it fine? Yeah.
It's fine.
Okay. Thank you. Any other question? No? Okay. Then we can interact and take a round of the department, right? Thank you.